So welcome to chapter 10. You will be happy to know that chapter 10 doesn't have any math in it, or very little anyways. So you get a little break from what we've been doing with chapter 9 with all the equations, the conversions. We're going to take a little break from that and discuss the states of matter. So conceptually, it's not too terrible either. We are going to add a little bit in because it's chemistry. You're in high school now. So we're not going to talk about states of matter just in the terms that you've discussed them over the years. We'll bring a lot of that up, but we're going to bring in today what's called the kinetic molecular theory. Okay. There are 5 lessons in this chapter. In the first one, we're going to introduce kinetic molecular theory and talk about gases. That's where it is the most obvious. Lesson 2, we are doing liquids. Lesson 3 is solids. 4 is changes of state. And then 5, we're going to talk specifically about water. Okay. So what I'll do for each of these is pretend like I'm actually talking to you. And since there's no math, I won't be working any problems. We'll just go through, I'll try to kind of give an explanation. Your book isn't the greatest at explaining this. So they kind of leave you still a little confused with some of the terminology that they use. So I'm going to try to be clearer than your book is. Just a little bit. Okay, so we're going to do the kinetic molecular theory, and you are welcome to abbreviate that in your notes. K-M would be pretty good. Okay. So the basics of kinetic molecular theory is that particles are always moving. That would be the kinetic part, right? So when you think of kinetic, you should automatically think of motion, either in terms of kinetic energy, which is really what they're describing here, or because you are who you are, and you're the generation that you are. Kinetic sand, right? It's that sand, you play with it, you move it around, you can mold it and shape it. So kinetic molecular theory is explaining molecules and particles and how they are in constant motion in terms of the energy, the kinetic energy that they have, and the forces that are acting between them. Okay, so the forces that are acting between the particles as they move. And basically, the more kinetic energy they have, the less force there is between the particles or between the molecules as they're moving around. Okay. This PowerPoint is posted, so if I'm going too quickly and you're not getting everything written down that you want to write down, you can go look at the PowerPoint online. Okay. So we're going to apply this theory specifically to gases today. And we're going to look at ideal gases. We're going to talk more about ideal gases in chapter 11, where we will do more math. I'm sorry to tell you, make sure you have a calculator. Saying that because when I'm making this video, it was your final. The other day I gave you your final and you didn't have calculators, and I told you to. Okay, so ideal gases are these hypothetical gases. They don't actually exist. They don't exist in nature, but they perfectly fit all of these assumptions of our theory. And there's 5 assumptions. Okay, so these 5 assumptions are that we have lots of particles. And in a gas, those particles are each very far apart compared to their size. Okay, so because these particles are very small, we might not really think of them as being far apart, but compared to their size, they are very far apart. Okay. The second assumption is that all of the collisions that they have, either between the particles themselves or between the particle and the wall of the container, are what we call elastic collisions. And this is a physics principle that we'll talk about next year. But elastic collisions mean that the 2 things hit and bounce apart, and there's no change to the total kinetic energy. And again, that doesn't really happen. That's a purely hypothetical thing. In nature, there's always some loss of energy. But for our purposes, we're going to say they don't lose any kinetic energy. They hit, they bounce away, and they have their same energy. Assumption 3 is that the particles are continuously moving. They're moving very quickly, and they're moving randomly. Okay, so by random, we mean they're not all moving the same direction as they move around. They're all going every which way. It's like, kindergartners when you take them outside and just take them outside and they just, okay. The fourth assumption, there's no attractive forces between the gas particles. And this comes from the fact that they're just moving. And they're moving so quickly that they can't stick together. Okay, and if they do hit, they have so much energy to them that they hit and bounce apart, kind of like if you're playing pool. Okay, your book says billiard balls. That's pool with like the stick. Yeah. Okay. And then finally, the fifth one is that the temperature is going to depend on the kinetic energy, the average kinetic energy. And we've talked about that before in other classes, that's how we define temperature, is the average kinetic energy of all the particles. The faster the particles are moving, the higher the temperature they'll have. And that has to do somewhat with like friction and energy. The more they're moving, the more heat they tend to generate. Okay, so the faster the particles are moving, the higher the temperature will be. Okay, so lighter gas particles tend to have higher higher speeds at the same temperature than a heavier particle because of the equation for kinetic energy. If you remember kinetic energy, nope, not on here. But the kinetic energy of anything is related to its mass and its velocity, and the equation is given in your book. Okay, it's 1/2 mv squared. You don't have to know it. We're not going to calculate it, I don't think. But because for this last point here, because the temperature depends on the average kinetic energy, and kinetic energy depends on both mass and speed. If you have two gases that are at the same temperature, the lighter gas particles will have a faster speed. Okay, in order to have the same temperature, because they have less mass, they would have to have higher speed. Okay, so let that sink in for just a minute. Okay, so those are the 5 principles of the kinetic molecular theory. They are the 5 assumptions. Okay, we're going to apply these to properties of gases. That's what we're doing next. So gases have these 5 properties. They can expand, and we've talked about that since about 2nd grade. Okay, gases fill whatever container you put them in. They take on that volume and shape of that container. Okay, so they can expand because they're moving rapidly in all directions. Okay, so the particles are moving all over the place. That's assumption number 3. Okay, and there's no attractive forces, no significant attractive forces between them because they're moving so quickly. Okay, and that one is assumption 4. Okay, so 3 and 4 are applying to the expansion. That's explaining why gases can expand to fill their containers. Gases are what we call a fluid. So most of the time when we say fluid, we think of liquids, but gases are also fluids because the particles move past one another. Okay, they're able to easily slide around one another. Again, because of assumption number 4, where there's no attractive forces between them. Okay, so liquids and gases have that same reasoning behind why they are called fluids, although liquids do have more of an attractive force. Okay, and we'll talk about that in the next lesson. Gases tend to have a very low density. Okay, so generally, I'm going to say generally because I am sure there is something out there where randomly the gas state is more dense than one of the others. and I just don't know that that exists. But typically, most gaseous substances at atmospheric pressure, and we'll talk about that and why that matters in chapter 11. But at atmospheric pressure, most gaseous substances, most things that are in the gaseous state, have a density that's about 1/1000th what it is in their liquid form. Okay. And that's just because their particles can spread out. That's assumption number one, right? That their particles in a gas are spread out so far compared to the size of the particles. Okay. The fourth property is that gases can compress. Again, because of assumption number one, that the particles are so far apart to begin with that there's a lot of space in between them, so we can squeeze them down, we can compress them. You can, I mean, you've probably done that if you've ever played with a balloon, right? If you think of like a water balloon, right, you can kind of squeeze on it and compress it a little bit, but not as much as like just a balloon filled with air. Okay, those you can really squeeze down. Okay, they will eventually pop, but you can squeeze them much further down. And then the last property is diffusion and effusion. So both of these have to do with the particles spreading out. Diffusion means that the particles are going to spread out in an area. So this is most obvious to you in terms of, I'm going to say using like a candle or something that smells really nice. If somebody sprays their, perfume or something in one area, it will eventually spread out across the room. Okay. That's diffusion. So the smell is coming from chemical particles. And so as it moves through the room, you can eventually smell it on the other side. Okay. Effusion is where particles are passing through a very tiny opening. So it's more like if you could take a balloon and just put a little a pinprick in it, just enough not to pop the whole balloon, but just enough that the air would start to escape. Okay, that's effusion. Okay, and effusion specifically refers to that those gases escaping into a vacuum, but we're going to use the other example as well. And so both of these principles are due to assumption number 3, the random motion of the particles. Okay, and we will come back a little bit to these ideas of diffusion and effusion in chapter 11. Again, at the end of chapter 11, we're going to revisit these and be able to describe kind of how quickly substances can move, these different gases can move. Okay, so you are going to be asked on your homework to explain each one of these in terms of the kinetic molecular theory or the assumptions of that theory. So revisit maybe make some notes or revisit your book or something, and it'll tell you which assumptions are explaining each one of these. Okay, so we said that the kinetic molecular theory is what we apply to ideal gases, and ideal gases don't really exist. Okay, so what about real gases? Like, why do we study this thing if it only applies to these ideal gases and they don't even exist in nature? Okay, they're totally hypothetical. So that gives us an idea of how gases should behave. And then we apply that to our real gases, the gases that actually exist, that don't behave completely according to these assumptions. And it's those deviations that we can actually learn a lot. Okay. So some gases, there are a handful of gases that if you get them at very high temperatures and low pressure, they get close to behaving ideally. or behaving like an ideal gas. So at lower temperatures and higher pressure, they would be very far from ideal. So at high temperature and low pressure, they tend to behave very close to an ideal gas. The more polar the molecules, now I'm bringing back this idea of polarity. Polar molecules are going to deviate more from ideal behavior, okay, and deviate more from the kinetic molecular theory. So if you remember polarity, polar, that was where in a molecule you have one atom that hogs the electrons. The electrons spend more time around one of the atoms than any of the others. So like in water, water is polar because the electrons spend more time with oxygen than with the hydrogens. Okay, so the more polar the molecule, the more it's going to deviate from that ideal behavior. So water would deviate, ammonia deviates a lot, but especially gases where you have like the exact same atom, like diatomic molecules, like nitrogen, right? Nitrogen and hydrogen, where we talked about, they always form, like you never find just one nitrogen, it's always going to be two, right? Diatomic, two atoms. They would be more likely to behave closer to your ideal because they're very nonpolar. Anytime you have two of the exact same element, it's going to be very nonpolar. They're going to pull equally on the electrons. Okay. So if you're confused about polar molecules, I would go back to about chapter 7, where we were talking about, or even it might even be a little further back than that. It might be back in like chapter 5, where we talked about nonpolar and polar molecules. It's one of those, it's somewhere in there, or you can look it up in the index, and that would tell you. Okay, so if you're still not really sure what makes a molecule polar, I'm going to suggest you go back and look at that in the book or in your notes from last semester, if you maybe still have those. I don't know. So that is the end of today's lesson on the kinetic molecular theory and gases. Okay, so we have these 5 assumptions of the kinetic molecular theory that we can apply to gases, and they explain the properties of gases. Specifically, they explain ideal gases, these hypothetical gases. But we can apply some of it to real gases and their behaviors, and use those to explain the behavior of real gases as well. Okay. So you have homework to do tonight, and we will move on. You should do lesson 2 tomorrow. Okay.